Hello everybody. So in the previous video, we went through a number of numericals, and here in this particular video, I'll be concentrating on one particular problem, which is slightly different when you compare it with the previous set of problems. So here, you have two loading systems given together. I mean, UVL is placed over UDL. UVL is placed over UDL. It's a compound loading system. I mean, you have two loading systems given together. You have UDL here. This is UDL. It is given in the rectangular form, and this is UVL. This is UVL. So this is a different type. This is a different type. And let us just analyze the loading system. Whenever you have UDL or UVL, you have to convert it back to point loads. So here you have two loading systems given together. This is what you're supposed to understand and analyze. This is problem number 10 in your notebook. This is the problem. So determine the support reaction for the beam shown in the figure. So this is the question given to you. See, if you just observe the rate of load distribution, it's given as 100 Newton per meter here and 300 Newton per meter here. So which is the rate of load distribution of UDL and which one is that of the next one, the UVL? You have two. This is UDL, uniformly distributed load, and this is UVL, given together, placed over one another. Now we need rate of load distribution in order to convert UDL or UVL or the combination into point loads. And since you have two loading systems kept over one another, you will get two point loads from this particular loading system. Now, in order to convert this combination into 2 point loads, we need rate of load distribution. It's 100 and 300. This particular point, the lower point is given as 100 and the upper point is given as 300. Let us try to analyze this particular system. And before that, again, you're supposed to find the support reactions or reaction offered by the supports here. Even in this particular case, you'll be finding the reaction offered by the support. Let us go step by step. So what is step number one? Step number one is to identify the type of support and mark support reactions. So this is a hinged support, So hinge support will offer two reactions. One in y direction, R-A-Y, and the other one in x direction, R-A-X. This is a roller support. So this offers only one reaction. This is R-B-Y. So done. So we have marked, and step number 2 is to draw the point load diagram. So before we draw the point load diagram, let me just consider this loading system separately. This is point A and this is point B. Let me consider the loading system separately, just to understand the loading system and just to convert these two into 2 point loads. Let me consider it separately and let me convert it. Now, the meaning of the rate of load distribution is in this way. See, this part from here to here, this is 100, the lower one. This is 100. So the rate of load distribution of UBL is 100, uniformly distributed load, or the lower part is 100. Rate of load distribution of the lower part is 100, and 300 is the entire rate of load distribution from this particular point to the lowermost point. So 300 includes the rate of load distribution of UDL as well, which is 100. Hope this is clear. I will make it clear here. See, this is 100. From here to here, it is 100. This is 100. But 300 is from bottom of this to the top. So 300 includes 100 as well. So 300 Newton per meter is the entire rate of load distribution, including UDL. So rate of load distribution of UDL, which is the lower part, is 100 Newton per meter. Rate of load distribution of UDL is 100 Newton per meter. Whereas 300 is not the rate of load distribution of UVL. 300 includes 100 as well. So this is 100. This is 100 in 300. 100 Newton per meter. So what is the rate of load distribution of the upper part, which is UVL? which will be 300 minus 100, which is 200 Newton per meter. So 100 Newton per meter is the rate of flow distribution of UDL. 200 Newton per meter is the rate of flow distribution of UVL. This is UVL. So when you have combination of UDL and UVL, just separate it. Separately find the rate of flow distribution. 100 is the rate of flow distribution of UDL and 300 minus 100. 300 has 100 included within it. So remove it off. So 300 minus 100 will be 200 and rate of flow distribution of UVL is 200. Now you have separately, you have divided it. You have divided UDL and UVL. So you have separated both. Done. So once you have separated both, you can convert it back to two point loads. Point load emerging from this UDL and point load emerging from this UVL. Let us convert. Let me help you to convert. I'm just concentrating on the loading system now. Let us do it step by step. Let me convert UVL, which is on the top. Let me convert UVL into a point load and then let me convert UDL. So let us first, we have separated it now. We have to convert it back to point loads. So let me consider UDL as it is. UDL as it is of 100 Newton per meter rate of load distribution. Now let me convert UVL, the upper part, which has a rate of flow distribution of 200 Newton per meter, which is uniformly varying, which is UVL. It's in the form of triangle. Now the point load, what you convert back from UVL, will act at a distance of 1/3 from the base and 2/3 from the apex. So this is the base and this is the apex. So 1/3 from the base, 1/3 of 4, and 2/3 from the apex, 2/3 of 4. 2/3 of 4, and the magnitude will be half into 200 into 4, half into 200 into 4. So this is the point load. This can be extended and drawn here as well. No issues. Done. So you have converted the upper part. Now you have the lower part to be converted back. Now let us convert back the lower part as well, which is UDL. So this is AB, and you have a point load already here, which is half into 200 into 4, and this is at a distance of 2/3 from the apex and 1/3 from the base. 2/3 of 4 and 1/3 of 4. Now we need a point load, another point load, which emerges from the other loading system, which is UDL, this loading system, with 100 Newton per meter as the rate of load distribution. So we'll get it here. The point load, what you convert back from UDL, will act exactly at the center. I will mark it here. Exactly at the center, in the sense this will be 2 meters and this will be 2 meters. And the magnitude of this load will be, I'll write it here, and the magnitude of this point load will be 100 into 4. That's it. 100 into 4. So you have 2 point loads here. This is one of the point loads with 100 into 4, which acts exactly at the center, 2 meters and 2 meters. This is the other point load with the magnitude half into 200 into 4, which acts at a distance of 2/3 from the apex and 1/3 from the base. These are the 2 point loads. Which you get from the combined loading system. This is how you get. So you have converted. I hope you are clear with the conversion. If you have 2 loading systems, UDL and UVL, given together. So if UDL and UVL are given together, one over another, you'll get 2 point loads. And this is how you convert. These are the 2 point loads. And let us draw the point load diagram. We have not yet drawn the point load diagram. Let me draw it for you. So this is point A and this is point B. So let us start from this particular point, which is C, and this particular point, which is D. Let us start from C now. C is the left extreme end. You have a force, a point load, which is inclined. And the angle of inclination is given as 135. This is just given to confuse. So see, if I extend this, if I draw an extension line, if this is 135, what would be this? This would be 45. Is it not? This angle would be 45. And let me draw it once again. See, if this is the force, 200 newtons, It should be resolved now. That's why I'm drawing it. This, if this is 135 degrees, this would be 45. This would be 45. Now let me apply the principle of transmissibility and push it to fourth quadrant. Push it to fourth quadrant. So this will be 45 degree and the magnitude is 200. So angle is indirectly given as 135 degrees. Hope this is clear. Now you have to resolve this force into its horizontal and vertical components. Horizontal component is this and vertical component is this. It acts exactly at C. So horizontal component will be 200 cos 45 and the vertical component is minus, which moves vertically downwards, minus 200 sin 45. Hope this is clear. Now coming to A, you have two forces acting at A. One is R, A, Y, and the horizontal forces R, A, X. Let me mark it here, R, X, because you have one more horizontal force of magnitude 200 cos 45. So in between A and B, you have these two forces, force number 1 and force number 2. Force number 1 and force number 2. So force number 1 acts exactly at the center, 2 meters and 2 meters. I'm just drawing it to indicate. And force number 2 acts at a distance of 2/3 from 4 and 1/3 from 4. Magnitude of this is half into 200 into 4. And the magnitude of this is 100 into 4. These are the 2 point loads available, which we have converted it from this particular from the combined loading system. And let us come to B now. At B, you have a single load of magnitude R, B, Y. And at D, you have an external moment of 500 Newton meter magnitude. An external moment which you are supposed to consider when you apply the third condition of equilibrium. So in this particular drawing, all the loads are in the form of point loads. All the loads are in the form of point loads. Now, after drawing the point load diagram, it's very simple. You'll be applying 3 conditions of equilibrium: summation of Fx equal to 0, Fy equal to 0, and moment either about A or B. A or B is this point here. This is A, and this is B. Not C and D, not the left extreme edges. Let me just take you through the calculation part. So this is how you convert UVL into a point load, and this is conversion of UDL. You get 2 point loads here. You get 2 point loads, and this is the point load diagram. It's written as free body diagram here. It's not the free body diagram. It's point load diagram itself, where you have all the forces in the form of non-concurrent force system. You have resolved this force as well, and you have 2 point loads. You have RB and you have an external moment of 500 Newton. It's not Newton per meter. It's Newton meter. So applying the conditions of equilibrium, summation of Fx equal to 0, you get Rax, which is the x, which is the reaction moving in x direction, plus 200 cos 45 is the resolved force of 200 Newton. So you'll get the value of Rax straight away. And summation of Fy equal to 0. Ray minus 200 sin 45 minus 400 minus 1. These two are the point loads which have converted from the combined loading system, plus RB by it is. So you'll get one equation. Apply the third condition. When you apply the third condition, make sure that you include this 500 Newton, which moves in clockwise direction, the external moment, and find the value of RB by, substitute the value of RB by in equation 1 to get the value of RA by, which is 385.47 Newtons. This is all about the calculation. Hope this particular problem is clear. So by this we complete the support reaction part. 70% of third module is done. 70% of third module is done, and the next part is stresses. We'll be covering it in the next video. Thank you.